how to do this, okay, then you can design a structure. If you don't know any, if there's any component that you don't know, okay, you cannot wholeheartedly design a structure. For this case, it looks simple. Not simple. For this case, you will realize, Eugene, if it is this case, right, a situation like this, a lot of times, why not we just use the normal stress? It's not so far away, right? If you look at the stress Z, and if you look at the value that we get over here, it's not so far away from stress Z, yes or no, right? That is what some engineers do. Okay, they just, okay, too difficult, I just calculate the maximum normal stress. That is very risky, because at one stage, this happened to have low shearing stress, right? If you have a structure that's a high shearing stress, you'll be in big trouble. Okay, you'll be in big trouble, right? Once a big shearing stress come in, then the principal stress will not be the same as stress what? Z. Okay. Now, I want to look at let's look at element B. Okay, as I said, I will show you this again. Okay, let's look at element B. Okay, so now I'm going to focus on element B. Okay, I'm not going to do more circle, but I'm just going to analyze the normal stresses and the shearing stress. Okay, so the next one, I'll do it again. So you see it one more time, maybe you'll feel more confident. So next we'll look at element B. Okay, and we are going to draw the orientation of element B. Okay, so like what I've done before. So over here now. Okay, so I'm going to copy this diagram. Okay, now we are going to look at element B. So we will know that this is our X, this is our Y, and this is our Z. So now we construct our element B. Okay, so this is how element B look like. Now you realize that element B, the in plane changes already, right? Right. So now when I say the word in plane, I know what that means. Yes or no? Right. So now we will know that. So now our in plane now is our YZ plane, right? Then our Y of out of plane is our XY plane, right? And then we know that this is our I'm having tongue tied now. XZ plane, right? So we know that this is our stress Z, right? I don't know whether these are right, but I'm going to call that. So this is my shear shear X Y, right? So it's going no, it's not shear X Y. The shear Y Z, sorry. Yeah. So that is our shear Z Y. Okay. Then this is our stress X. This will be our stress Y. Okay. So now coming back, we will know that stress X is equal to 0, and it also have 0 shearing stress. Okay. Stress Z, we don't know, and we know we have shear ZY. Stress Y, we know is 0, and it also have a shear YZ. We know that. Okay. So from here, we have to find our stress Z. Okay. So stress Z, we just write up the formula again. Now, I've not done this in a long time, right? I've shown you 1.5 hours ago. What is it? Now I forget all the numbers. Okay, so we are doing. So we know that this is px over a, right? We know that this is x over ixx multiplied by y, and this is my over iyy multiplied by x. Okay, so we know that the px is compression. Now mx, I have not a clue. Okay, so we go back, we look at mx. Okay, this is my, look at mx. Did we write anything? I hope we did. So for mx, all right, so this is moment about x, mx, yay, is equal to 0, right? Because it's at the centroid due to mx. So this is equal to 0. So you just cancel. This is equal to 0. This is equal to 0. Right? I can cancel this out. Okay? We don't need to consider it. We should need. That's why analyzing the data, the element stress is so important. You know why? Because I'll tell you this. I've been blabbing for close to 2 hours. My brain is dead now. Okay? My brain is dead now. Then we have my. Okay? So my, it is positive. You can see that. Right? And it's 9600. So now we know that this is positive. Okay, this is positive. Okay, so this will be equal to minus by, what is our axial load? Our axial load, sorry, I'll be flipping over. It's 100 times 10 to the power 3. The area is equal to 5320. Plus by my. Okay, so my is 9600 divide by iyy. Okay, I don't know what is our iyy anymore. Divide iyy. So iyy is 9.03 times 10 to the power minus 6. Now the thing is, what is our x distance? Okay, again, it can be confusing at times, and now I'm so confused also. Okay, so so x distance, I'm going to copy this. Okay, I'm going to paste here. Right, I'm going to string it down. Right. Okay, so element B is here. Okay, element B is here. Right, that is our element B. So the x, so x distance is usually distance in this way. Right, and we know that we need the x distance. So we need to find what is TW, and then we don't divide by 2. Okay, so TW divided by 7.24. Okay, 7.24 is our TW. So this is equal to 7.24 times 10 to the power minus 3 divided by 2. Okay, so this will be equal to minus 100 power 3 divided by 320 power minus 6 is equal to minus 18.797 times 10 to the power 6. Let me do it again. 100 power 3 divided by 5320 power minus 6. Yep, 18.796, and that will be 7.24 power minus 3 divided by 2 times by 9600 divided by 9.03 power minus 6 is equal to 3. So plus by 3.849. Okay, so 9600 times 7.24 power minus 3 divided by 2. divided by 9.03 power of minus 6, 3.849. Okay, so minus 18.797 power of 6 plus by 3.849 power of 6 is equal to 14. So minus 14.948 times 10 to the power 6 Pascal. Let me do it again. Minus 18.797 power 6 plus 3.849 power 6. Yep, 14. So we now know our stress Z. Okay, so we know that this is 14.948. Okay, and then next we are going to find out our stress, our shearing stress. Okay, so we are going to find our shearing stress. Hold on. We're going to find our shearing stress due to Vx first. Okay, so this is Vx. Then I'm going to copy the diagram across. And we have good news. Okay, so we know that Vx, right, is heading this direction. So this is 16 times 10 power 3, right? So when we construct the shear flow, right, it will come in. And at the center out, you got one arrow coming, one arrow going out. So it states that what? Okay, so Vx, so we know that the shear or the Qx, or if we look at the formula, shear xz is equal to Vx over Iyy Qy, right, divided by T, right? So it's at the center over here, right? Qy is equal to 0. Because at the center over here where both meet is a what? It's also a terminal, yes or no? Right? Because both of them meet in the center. When the arrow from the top and the arrow on bottom come in the center, they meet, is equal to what? It's equal to 0. Right? Like if you look at in a box beam, if you look at the analysis of a box beam, just to quickly recap, if you have V coming here, right, it goes out. And then when it comes to here, when left and right meets, the Q is also equal to 0, yes or no? So this over here, at the top, Q is equal to 0, at the bottom, Q is 0, at that point. So for this case, Qy is equal to 0. So therefore, okay, it's equal to 0 due to what? Due to Vx. Okay, and I think we did this before. Okay, so let me save some space. Okay, so that is due to Vx. So if we look at our analysis on Vx, do we have it? No, that is Vy. They have Vx. And we say point B is equal to what? 0. We did have it. Okay. So next we go for the shearing stress due to I think I got my thing wrong. This is due to no. Wait. Undo. Wrong page. Am I in the wrong page? Yeah, wrong page. Woo! They look the same. Then the next one we're going to find all right, we're going to find due to Vy. Okay. I think this example is going to is a very good revision. Yeah, I think it's a very good revision. I know some of you are tired, so am I. Okay, I'm kaput now. Okay, so this is your Vy, right? So for this case, you have to consider